And now in this lecture we'll answer two questions. In the first question we find out the area of this rectangle ABCD, and in the second question we find out the area of this green shape that is inside square ABCD. So we start with the first question. In the drawing we have rectangle ABCD. Inside this rectangle we have this semicircle. In addition, we know that this is the line 7 PC, that is equals to 5 units in its length. This is called AP, that is equals to 6 units in its length. Again, our mission is to find out the area of this rectangle ABCD. So first of all, because of the fact that ABCD is a rectangle, all those four angles are all right angles. So this is a right angle. This is a right angle. This is a right angle. And this is also a right angle. So in the next step, we define the center of this semicircle. This point is point O, and we define the radius of this semicircle as x. In addition, we define the touching point of this semicircle with side AB of this rectangle ABCD. This point is point E. And finally, we will define the point of tendency of tangent DC with this semicircle. This point is point M. In the next step, we join points O and M together on a straight line. Point O is the center of the semicircle. Point M is the point on the semicircle itself. Therefore, OM is the radius of this semicircle. Is equals to x. Likewise, OA is also the radius of the semicircle, is equals to x, and OE is also the radius of the semicircle, is equals to x. The radius OM that is equals to x, the radius OM is drawn to point M, that is the point of tendency of tangent DC in this semicircle. And whenever your radius is drawn to the point of tendency, then tangent DC will be perpendicular to the radius MO. If DC is perpendicular to MO, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to rule 1. So by doing this construction, we can do the small quadrangle DAOM. Inside this small quadrangle DAOM, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees. So 270 degrees plus the size of this floor facing angle, in total they must be equal to 360 degrees according to the rule that says that the sum of the angles in any quadrangle is equal to 360 degrees. Therefore this floor facing angle must be equal to 90 degrees in its size. So inside the small quadrangle DMOA we have 4 right angles, and according to rule 5, any quadrangle that has 4 right angles must be this rectangle in front of square. So we relate to this small quadrangle DMOA is rectangle because it has 4 right angles. But we also know that the opposite sides of rectangle are equal to each other. So in the small rectangle DAOM, side MO must be equal to the opposite side DA, but MO is x, therefore the opposite side DA must be also equal to x units in its length. The opposite sides of a rectangle are equal to each other also in the big rectangle ABCD. That is to say, side DA side DA must be equal to the opposite side CB in rectangle ABCD. In the big rectangle ABCD. But DA equals to X, therefore the opposite side CB must be also equal to X units in its length. In the next step, we join points P and E together by straight line. By joining points P and E, we can get peripheral angle APE. This is peripheral angle APE that subtends on AE, that is the diameter of this semicircle, and we know that any peripheral angle that subtends on the diameter of a semicircle or a circle, it must be equal to 90 degrees in its size. Therefore, this peripheral angle APE must be equal to 90 degrees, according to rule 7. So, I'll repeat quickly on rule 7. According to rule 7, if a peripheral angle subtends on the diameter of the circle, then it is equal to 90 degrees in its size. So in the drawing we have a circle, chord AB, it is the diameter of this circle. This is peripheral angle ACB that subtends on AB, that is the diameter of this circle, and therefore peripheral angle ACB must be equal to 90 degrees in its size according to this rule, rule 7. We have already implemented rule 7 in our drawing. One to our drawing. This is peripheral angle APE that subtends on AE, that is the diameter of this semicircle, and therefore according to rule 7, peripheral angle APE must be equal to 90 degrees in its size. In the next step, we define this angle as alpha, and in the right triangle APE, this angle equals to alpha, this angle equals to 90 degrees, therefore this first angle must be equal to 90 degrees minus alpha. Why? Because 90 degrees minus alpha plus alpha is 90 degrees, and 90 degrees plus 90 degrees is equal to 180 degrees, that is the sum of the angles in any triangle. Likewise, in the big right triangle ABC, this angle equals to alpha, this angle equals to 90 degrees, therefore this third missing angle must be equal to 90 degrees minus alpha. According to the sum rule, that says that the sum of the angles in any triangle is equal to 180 degrees. So in the next step, we'll prove that this right big triangle ABC is similar to this right small triangle APE. Okay, so I'll write it down. We prove that the right big triangle ABC is similar to this right small triangle APE. This is the small right triangle APE. So why the big right triangle ABC is similar to this small right triangle APE? First of all, this is angle A, that is a common angle that belongs to both triangles. Angle A belongs to the big right triangle ABC, and angle A belongs also to the small right triangle APE. So we can write down that angle A equals to itself is a common angle that belongs to both triangles. So if we relate to this angle A, it belongs to the right triangle ABC, it will be defined as angle CAB. And angle A equals to itself, so if we relate to angle A, since it belongs to the right small triangle APE, it will be defined as angle PAE. So repeat again. This equation means that angle A equals to itself. We just called to angle A two different names. Angle A equals to itself is a common angle that belongs to both triangles. In addition, those two angles are both equal to 90 degrees, therefore they are equal to each other. So actually this is angle ABC in the right big triangle ABC, and it is equal to this angle, that is actually angle APE in the right small triangle APE. So repeat again. Angle ABC in the big right triangle ABC equals to angle APE in the right small triangle APE. They are both equal to 90 degrees and therefore they are equal to each other. And finally, those two angles, they are both equal to 90 degrees minus alpha, therefore they are equal to each other. So actually, this is angle ACB. In the right big triangle ABC, and it is equal to this angle, that is actually angle PEA. In the right small triangle APE. I'll repeat again. I should found out that angle ACB in the big right triangle ABC equals to angle PEA in the right small triangle APA. They are both equal to 90 degrees minus alpha, therefore they are equal to each other. So actually found that all the triangles of the right big triangle ABC are correspondingly equal to all the triangles of this right small triangle APE. Therefore, those two right triangles are similar to each other according to angle similarity rule. So I write it down. If we found out that the right big triangle ABC is similar, this is the sum of similar to the right small triangle APE according to angle similarity rule. And from the fact that those two right triangles are similar to each other, we will derive that the following relationship exists between their sides. We will derive that side AP of the right small triangle APE over side AB of the right big triangle ABC is equal to side AE of the right small triangle APE over side AC of the big right triangle ABC. So repeat again. From the fact that those two right triangles are similar to each other, we will derive that the following relationship exists between their sides. Side AP of the right small triangle APE over side AB of the right big triangle ABC is equal to side AE of the small right triangle APE over side AC of the big right triangle ABC. AP equals to 6 units in its length according to what is given as the question, over AB. AB is the missing side, so we leave it as it is, and it is equal to AE. AE is the diameter of this semicircle, that is equal to 2x. Over AC. AC in total equals to 6 plus 5, that is 11. So in total, we shall find out that 6 over AB equals to 2x over 11. Here we will cross multiply this equation. And we get that 6 times 11 is 66, and it is equal to 2x times AB. So 66 equals to 2x times AB. Here we will divide this equation by 2, and get that 66 over 2 is 33, and it is equal to 2x over 2 is x, so in total this expression equals to x times AB. So if we found out that 33 equals to x times AB, here we divide this equation by x, and we get that 33 over x equals to AB. So AB equals to 33 over x units in its length. So actually, this is side AB of rectangle ABCD, and it is equal to 33 over x units in its length. Our mission is to find out the area of this rectangle ABCD. So what is the area of this rectangle ABCD? Actually, we know that the area of any rectangle equals to the length of the rectangle times the width. Okay, then the area of any rectangle equals to the length of the rectangle times the width. And therefore, the area of this rectangle ABCD must be equal to the length of this rectangle ABCD times the width. The length of this rectangle ABCD is AB, and the width is CB. So in total, we shall find out that the area of this rectangle ABCD equals to AB times CB. AB is 33 over x, and CB equals to x. So we have here x in the numerator and x in the denominator, so x will get cancelled, and we left only with 33. So now we should find out that the area of this rectangle ABCD, that is the area that we are looking for in this question, is equal to 33 square units. The area of rectangle ABCD is equal to 33 square units. And that is the answer to the first question. So in the next step, I will present you the second question, and we will solve the second question of this lecture. Our mission in this second question is to find out the area of this green shape. So in the drawing, we have square ABCD. This is square ABCD. In addition, we know that line segment BP equals to line segment PC. And finally, we also know that this is triangle OPC. The size of this triangle OPC is 5 square units. Again, our mission is to find out the area of this green shape. So first of all, we define the length of this line segment BP as A. And because of the fact that BP equals to PC and BP equals to A, therefore PC must be also equal to A. We also know that all the sides of an rectangle are equal to each other. So in this rectangle ABCD, side BC equals to A plus A, that is 2A. Therefore the opposite side AD must be also equal to 2A units in its length. Those two angles are defined as vertex angles, and we know that vertex angles are equal to each other. So if we define the size of this vertex angle as theta, then this vertex angle must be also equal to theta because they are equal to each other according to the rule that I mentioned. We also know that the opposite sides of a square are parallel to each other. So in square ABCD, side AD is parallel to the opposite side BC. Side AD is parallel to the opposite side BC. Those two angles are defined as alternating angles and are located between the parallel lines AD and BC. And according to Rule 15, alternating angles between parallel lines are equal to each other. So those two alternating angles that are located between the parallel lines AD and BC must be equal to each other according to Rule 15. So if we define the side of this alternating angle as alpha, then the side of this alternating angle must be also equal to alpha because they are equal to each other according to Rule 15. Likewise, those two angles are also defined as alternating angles and they are located between the same parallel lines AD and BC. Therefore, they must be equal to each other according to the same rule, Rule 15. So if we define the side of this alternating angle as beta, then the side of this alternating angle must be also equal to beta because they are equal to each other according to Rule 15. So actually found out that those two triangles are similar to each other according to angle similarity rule. That is to say, in both triangles we have angle theta, in both triangles we have angle alpha, and in both triangles we have angle beta. Therefore, those two triangles are similar to each other according to angle similarity rule. So I write it down. So 3. This is the big triangle AOD. And it's similar, this is the sign of similar to this small triangle POC. According to angle similarity rule. So repeat again, we actually found out that the big triangle AOD is similar to the small triangle POC according to angle similarity rule. So in the next step, I will present to you a new rule that relates to similar triangles, and we will implement the new rule in our drawing on those two similar triangles AOD and POC. The new rule is Rule 22. According to the new rule, Rule 22, the ratio between the areas of similar triangles is equal to the square of the ratio of their corresponding sides. So in the drawing we have those two similar triangles. This is triangle ABC that is similar to this triangle DEF. And according to this rule, Rule 22, the ratio between the areas of those two similar triangles, that is to say, what is the ratio between the areas of those two similar triangles? It's actually the area of triangle ABC over the area of triangle EDF. So that ratio, this ratio, is equal to the ratio between the square of the ratio of their corresponding sides. So what is the square of the ratio of their corresponding sides? On those two triangles, side AC is the corresponding side of side DE. Likewise, side AB is the corresponding side of side DF, and this is side CB, that is the corresponding side of side EF. So again, side AC is the corresponding side of side DF. again, side AC is the corresponding side of side DE. So the square of the ratio of those two corresponding sides is AC over DE squared. Again, the square of the ratio of those two corresponding sides is AC over DE squared. AC over DE squared. So the ratio between the areas of those two triangles, this is actually the area of triangle ABC over the area of triangle EDF. That ratio is equal to the square of the ratio of their corresponding sides. That is to say, it is AC squared over DE squared. Likewise, AB is the corresponding side of side DF. So the square of the ratio of those two corresponding sides is AB over DF squared. AB over DF squared. And finally, side CB is the corresponding side of side EF. So, and the square of the ratio of those two corresponding sides is of course CB over EF squared. Okay. So we can implement Rule 22 in our drawing. Why? Because in our drawing we have already found out that the big triangle ADO is similar to this small triangle OCP. Again, the big triangle AOD is similar to this small triangle COP. So whenever you have two similar triangles, you can implement Rule 22. So according to Rule 22, the ratio between the areas of those two similar triangles, what is the ratio between the areas of those two similar triangles? It's actually the area of this triangle ADO, the big triangle ADO, over the area of this small triangle COP. Repeat again, the ratio between the area of those two similar triangles is equal to the area of the big triangle ADO over the area of the small triangle COP. That is the ratio between the areas of those two similar triangles. That ratio is equal to the square of the ratio of their corresponding sides. In these two similar triangles, side AD is the corresponding side of side PC. Why side AD is the corresponding side of side PC? Because of the fact that side AD is in front of this angle theta, and likewise this is side PC that is in front of the same angle theta. Therefore, side AD is the corresponding side of side PC. And the square of the ratio of those two corresponding sides is of course AD over PC squared. AD over PC squared. So this equation is the implementation of Rule 22 in our drawing. According to this equation, the square of the ratio of those two, the ratio between the areas of those two similar triangles, that is actually, what is the ratio between the areas of those two similar triangles? It is actually the area of the big triangle ADO over the area of triangle COP. And that ratio is equal to the square of the ratio of their corresponding sides. Here side AD is the corresponding side of side PC, and the square of the ratio of those two corresponding sides is AD over PC squared. AD over PC squared. Okay? So here the area of triangle ADO. The area of this big triangle ADO is unknown, so we leave it as it is. Over the area of the small triangle COP. The area of this small triangle COP is equal to 5 square units according to what is given as the question. So we substitute the area of this small triangle COP by 5. And it is equal to AD over PC squared. AD is 2A and PC is A. So it is 2A over A squared. We have A in the denominator and A in the denominator, so A will get cancelled, and we left only with 2 squared, that is 4. So in total, we found out that the area of the big triangle ADO over 5 is equal to 4. So here we multiply this equation by 5, and we get that the area of the big triangle ADO is equal to 5 times 4, that is 20 square units. So we can find out that the area of this big triangle ADO is equal to 20 square units. Those two triangles are similar to each other, and therefore the following relationship exists between their sides. Side AD of this big triangle ADO over side PC of this small triangle POC is equal to side AO of this big right triangle AOD over side OC of this small triangle POC. So I repeat again, because of the fact that those two triangles are similar to each other, the following relationship exists between their sides. Side AD of the big triangle ADO over side PC of the small side AD of the big triangle ADO over side PC of the small triangle POC is equal to side AO of the big triangle AOD over side OC of the small triangle POC. AD equals to 2A and PC equals to A. So 2A over A equals to AO over OC. So we have here A in the denominator and A in the denominator, so A will get cancelled and we're left only with 2. So in total we shall find out that 2 equals to AO over OC. So here we multiply the equation by OC and we get that 2 times OC equals to AO. And again, if we find out that 2 times OC equals to AO. So here we define the length of this line segment OC or side OC as B, and we substitute OC in this equation by B, and we get that 2B equals to AO. So if we found out that if we define the length of line segment OC as B, then AO will be equal to 2B. That is to say, AO is twice as long as OC. So if we define the length of this line segment OC as B, then the length of this line segment AO is equal to 2B. So in the next step, I present to you a new rule, and we implement the new rule in our drawing. The new rule is rule 23. According to rule 23, first of all, rule 23 is true in any triangle. So this is triangle ABC that could be any triangle. In this triangle ABC, if we draw the red line segment AP, we divide this big triangle ABC into 2 smaller triangles. The first small triangle is triangle ABP, and the second small triangle is triangle APC. So rule 23 is about those 2 small triangles that were created by drawing line segment AP and triangle ABC. And according to rule 23, the ratio between the areas of those 2 triangles is equal to the ratio between their corresponding bases. So the ratio, what is the ratio between the areas of those two triangles? It is actually the area of triangle ABP over the area of triangle APC. Again, this is the ratio between the areas of those two small triangles, and that ratio is equal to the ratio between their corresponding bases. The base of this triangle ABP is BP, and the base of this triangle, the small triangle APC, is PC. And the ratio between their bases is, of course, BP over PC. So the ratio between the areas of those two small triangles, that is the area of triangle ABP over the area of triangle APC, equals to the ratio between their corresponding bases, that is BP over CP. But how we arrived to this equation, because the area of this small triangle ABP is the base of triangle ABP times the height over 2. So it is BP times the height, that is h, over 2. That is actually the area of this small triangle ABP over the area of triangle APC. What is the area of this triangle APC? It is the base PC times the height h. They have the same height, divided by 2. Again, it is the base PC times the height h over 2. So the ratio between the areas of those two triangles is, of course, the ratio between those two expressions. This is actually BP times h over 2 times CP times h over 2. That's actually the ratio between the areas of those two small triangles. So here we have 1/2 in the numerator and 1/2 in the denominator. So 1/2 will get cancelled, and we also have h in the numerator and h in the denominator, so h also will get cancelled, and we left only with BP over CP. Therefore, we actually found out that indeed the ratio between the areas of those two small triangles is equal to the ratio between their corresponding bases, because the ratio, the base of this triangle ABP is BP, and the base of this triangle APC is PC, and the ratio between their bases is BP over CP. So in total, we actually found out that the ratio between the areas of those two small triangles, that is the area of triangle ABP over the area of triangle APC, is indeed equals to the ratio between their corresponding bases, that is BP over PC. Because BP is the base of triangle APC, and PC is the base of this triangle APC. Okay, so we can actually implement Rule 23 in our drawing. Why? Because in our drawing, this is the big right triangle ADC. And we have here, this is 97DO that divides this big right triangle ADC into two small triangles. Those are the small triangles that 97DO divides the big right triangle ADC. The first small triangle is this triangle AOD, and the second small triangle is triangle DOC. And according to Rule 23, so actually all the requirements of Rule 23 are satisfied, and therefore we can implement here Rule 23. According to Rule 23, the ratio between the areas of those two small triangles, that is actually the area of this big triangle, the area of this triangle ADO, over the area of this triangle DOC. So the ratio between the areas of those two small triangles is equal to the area of triangle ADO over the area of triangle DOC. That ratio is equal to the ratio between their corresponding bases. That is to say, it is AO over OC. AO over OC. And again, the ratio between the areas of those two small triangles, it is actually the area of triangle ADO over the area of triangle DOC. And that ratio is equal to the ratio between the corresponding bases. It is actually AO times OC. AO over OC. So why this equation is true? I already proved that this equation is true. But anyway, I will prove it again. I will just draw the big triangle ADC, and I will prove that this equation is true. So actually, this is the big right triangle ADC that is coming from the original drawing, and this is the red line 70 that is coming from here. So from point D, we draw perpendicular on AC. Again, from point D, we draw perpendicular on AC. So actually, this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. And we define the height, this height, as h. It is the height to side AC. So, according to Rule 23, the area of triangle ADO over the area of triangle DOC equals to AO over OC. So, what is the area of triangle AOD? It is equals to the base AO times the height, that is h, over 2. The area of this triangle AOD, it is equals to the base AO times the height h, over 2. Triangle AOD is equal to the base AO times the height, that is h, over 2. Likewise, what is the area of this triangle AOD? The area of this triangle AOD is equal to we found out that this triangle AOD is equal to the base AO times the height h, over 2. So what is the area of this triangle COD? The area of this triangle COD, it is equal to the base, that is CO. So what is the area of this triangle DOC? The area of triangle DOC is equal to the base, that is actually OC, times the height. They have the same height, that is h, divided by 2. And the area of triangle AOD over the area of triangle DOC is the ratio between those two expressions. So here we have h in the numerator and h in the denominator, so h will get cancelled. And we also have 2 in the denominator, so, and 2 in the numerator here, so 2 also get cancelled. and we're left only with AO over OC. So we found out that the ratio between the areas of those two small triangles, that's actually the area of triangle AOD over the area of triangle OC is equal to the ratio between their corresponding vessels. This is actually AO over OC. Exactly like this equation is actually the same equation. The area of triangle AOD over the area of triangle DOC is equal to AO over OC. The area of triangle AOD over the area of triangle DOC equals to AO over OC. Okay? So I prove that this equation is true. So copy again the equation according to rule 23. We shall find out that the area of triangle ADO over the area of the small triangle DOC is equal to AO over OC. Repeat again, according to rule 23, I shall find out that the area of triangle AOD over the area of triangle DOC equals to AO over OC. The area of triangle AOD, the area of this triangle AOD is 20, so let's do the area of triangle AOD by 20 over the area of this triangle DOC. The area of this triangle DOC is unknown, so we leave it as it is. And it is equals to AO over OC. AO is 2B and OC is B. So AO is 2B and OC is B. So we have here B in the numerator and B in the denominator, so B will get cancelled and we left only with 2. So in total we found out that 20 over the area of triangle DOC is equal to 2. So here we multiply this equation by the area of triangle DOC and we get that 20 equals to 2 times the area of triangle DOC. So 20 equals to 2 times the area of triangle DOC. Here we divide this equation by 2. And finally we get that the area of triangle DOC is equal to 20 over 2 is 10 square units. So if we found out that the area of this small triangle DOC is equal to 10 square units. It is very easy to see from knowing that this is the right triangle BOC, this is triangle ABC, and this triangle ABC can point to this triangle ADC according to side rule. Repeat again, this triangle ABC can point to this triangle ADC according to side rule. So why those two triangles can point to each other? First of all, side AB of triangle ABC over side AB of this triangle ABC is equal to side DC of triangle ADC because ABCD is a square. Likewise, side BC of triangle ABC is equal to side AD of triangle ADC because of the fact that AD is a square. And finally, side AC is the common side that belongs to both triangles, so we can write down that AC equals to itself is a common side that belongs to both triangles. So we should find out that that this triangle ABC can point to this triangle ADC according to side rule. the right triangle ABC congruent, this is the sign of congruent, to the right triangle ADC according to side rule. And from the fact that those two right triangles can go into each other, we derive that they have also the same areas. That is to say, the area of this triangle ABC is equal to the area of this triangle ADC. So I write it down. The area of triangle ABC is equal to the area of triangle ADC. Any two triangles that can go into each other, they must have also the same areas. But it is very easy to see from the drawing that the area of this right triangle ADC in total it is equal to 20 plus 10, that is 30 square units. So we can write here that the area of the right triangle ADC is equal to 30 square units. And from this equation, the area of triangle ABC is equal to the area of triangle ADC equals to 30. We derive that the area of triangle ABC is also equal to 30 square units. From one side, but from the other side, the area of this triangle ABC, the area of this big right triangle ABC is equal to the area of this green shape plus the area of this triangle COP, that is 5 square units. So we define the area of this green shape, that is the area that we are looking for in this question, as x. That is to say, the area of this green shape is equal to x square units according to our definition. So in total, from the other side, the area of this big right triangle ABC is equal in total to x plus 5 square units. So from the other side, the area of the big right triangle ABC is equal to x plus 5 square units. And from this equation, x plus 5 equals to the area of triangle ABC equals to 30. We derive that x plus 5 equals to 30. So x plus 5 equals to 30. X is the area of the green shape. So we subtract 5 from this equation, and we get that x, that is the area of the green shape, that is the area that we are looking for, is equal to 30 minus 5 is 25 square units. So if we found out that the area of the green shape is equal to 25 square units, and that is the answer to the second question. Repeat again, if we found out that the area of this green shape is equal to 25 square units. So we finish with the second question. In the next step, I'll summarize the next step. We'll start with the first question, of course. Our mission in this first question is to find out the area of this rectangle ABCD. So in the drawing we have a rectangle ABCD. Inside this rectangle we have this semicircle. In addition, we know that this is called AP, that is equals to 6 units in its length. This is line segment PC, that is equals to 5 units in its length. Again, our mission is to find out the area of this rectangle ABCD. So first of all, because of the fact that ABCD is a rectangle, all those 4 angles inside rectangle ABCD are right angles. In the next step we define the center of this semicircle. This point is point O. We define the radius of this semicircle as x. We define the touching point of this semicircle with side AB of rectangle ABCD. This point is point E. And we define the point of tendency of tangent DC with this semicircle. This point is point M. Point O is the center of the semicircle. Point A is the point of the semicircle itself. Therefore, OA is the radius of the semicircle. This is equal to x units in its length according to our definition. Likewise, OE is also the radius of the semicircle. This is equal to x. We join points O and M together by straight line. OM is of course the radius of this semicircle. That is equals to x. And because of the fact that the radius OM that is equals to x, the radius OM is drawn to point M, that is the point of tendency of tangent DC with this semicircle. And whenever you have a radius that is drawn to the point of tendency, then tangent DC will be perpendicular to the radius MO. If this is perpendicular to MO, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees, according to rule 1. By doing this construction, we get the small quadrilateral DMOA. Inside this small quadrilateral DMOA, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees, so 270 degrees plus the size of this 4-piece angle. In total, it must be equal to 360 degrees. According to the rule that says that the sum of the angles in any quadrilateral is equal to 360 degrees. Therefore, this 4-piece angle must be equal to 90 degrees in its size. So inside the small quadrilateral DMOA, we have 4 right angles, and according to rule 5, any quadrilateral that has 4 right angles must be its rectangle if not a square. So relate to this small quadrilateral DMOA, it's a rectangle because it has 4 right angles. But we also know that the opposite sides of a rectangle are equal to each other. So in the small rectangle DMOA, side DA must be equal to the opposite side MO. But MO is x, therefore the opposite side DA must be also equal to x units in its length. Likewise, in the big rectangle ABCD, the opposite sides must be also equal to each other. That is to say, side DA must be equal to the opposite side CB. But DA is x, therefore the opposite side CB must be also equal to x units in its length. In the next step, we join points P and E together by straight line. By joining points P and E, we get a peripheral angle APE. This is peripheral angle APE that subtends on AE, that is the diameter of this semicircle. And you know that according to rule 7, any peripheral angle that subtends on the diameter of the circle or semicircle must be equal to 90 degrees in its size. Therefore, this peripheral angle must be equal to 90 degrees according to rule 7. In the next step, we define this angle as alpha. So in the right small triangle APE, this angle equals to alpha. This angle equals to 90 degrees, and therefore this third angle must be equal to 90 degrees minus alpha. Why? Because 90 degrees minus alpha plus alpha is 90 degrees, and 90 degrees plus 90 degrees, it is equal to 180 degrees. That is the sum of the angles in any triangle. Likewise, in the big right triangle ABC, this angle equals to alpha, this angle equals to 90 degrees, therefore this third angle must be equal to 90 degrees minus alpha according to the sum rule that said that the sum of the angles in any triangle is equal to 180 degrees. In the next step, we prove that the big right triangle ABC is similar to this small right triangle APE. So why those two right triangles are similar to each other? First of all, this is angle A, that is the common angle that belongs to both triangles. Angle A belongs to the big right triangle ABC, and angle A also belongs to the small right triangle AP. So angle A equals to itself is the common angle that belongs to both triangles. In addition, those two angles are both equal to 90 degrees, and therefore they are equal to each other. And finally, those two angles are both equal to 90 degrees minus alpha, therefore they are equal to each other. So in total, we found out that all the angles of the right big triangle ABC are correspondingly equal to all the angles of this right small triangle AP. And therefore, those two right triangles are similar to each other according to angle similarity rule. And again, we found out that the right big triangle ABC is similar to the right small triangle AP according to angle similarity rule. And for the fact that those two right triangles are similar to each other, we derive that the following relationship exists between their sides. That side AP of the right small triangle APE over side AB of the big right triangle ABC is equal to side AE of the small right triangle APE or side AC of the big right triangle ABC. Okay, repeat again. Side AP of the small right triangle APE over side AB of the big right triangle ABC equals to side AE of the small right triangle APE over side AC of the big right triangle ABC. AP is 6, according to what is given in the question, over AB. AB is the missing side, so we limit as it is, and it is equals to AE. AE is the diameter of the semicircle, that is 2x, over AC. AC in total equals to 6 plus 5, that is 11. So in total, we have found that 6 over AB equals to 2x over 11. Here, of course, multiply this equation, and finally found out that 6 times 11, that is 66, equals to 2x times AB. Here we divided this equation by 2 and finally found out that 66 over 2 is 33, so 33 equals to x times AB. Here we divided this equation by x and finally found out that AB equals to 33 over x. So the length of this side AB of rectangle ABCD is equal to 33 over x. Our mission is to find out the area of this rectangle ABCD. So what is the area of rectangle ABCD? Actually we know that the area of any rectangle equals to the length of the rectangle times the width. And therefore the area of this rectangle ABCD must be equal to the length of this rectangle ABCD times the width. The length of this rectangle ABCD is AB and the width is BC. So in total the area of rectangle ABCD must be equal to AB times CB. AB is 33 over x and CB is x. So in total we found out that the area of rectangle ABCD equals to 33 over x times x. You have x in the numerator and x in the denominator, so x will get cancelled and we left only with 33. So we found out that the area of this rectangle ABCD is equal to 33 square roots. So we finish with the first question. In the next step, I presented to you the second question and we solved the second question of this lecture. Our mission in this second question is to find out the area of this range shape. So in the drawing we have square ABCD. We know that this is line segment VP, that is equals to this line segment PC, and this is line POC, that is equals to 5 square units in its size. Again, our mission is to find out the area of this range shape. First of all, we define the length of this line segment BP as A. BP equals to PC, therefore PC must be also equal to A. We know that all the sides of a square are equal to each other, therefore side AD is equal to the opposite side BC. BC equals to 2A, therefore AD must be also equal to 2A. Those two angles are defined as vertex angles, and we know that vertex angles are equal to each other. So if the size of this vertex angle is theta, then the size of this vertex angles must be equal to theta because they are equal to each other according to the one dimension. We also know that the opposite sides of a square are parallel to each other. So in square ABCD, side AD side AD is parallel to the opposite side BC. Those two angles are defined as alternating angles and they are located between the parallel lines AD and BC, and therefore they are equal to each other according to Rule 15. According to Rule 15, alternating angles between parallel lines are equal to each other. So if you define the size of this angle as alpha, then the size of this angle must be also equal to alpha because they are equal to each other according to Rule 15. Likewise, those two angles are also defined as alternating angles and they are located between the same parallel lines AD and BC, and therefore they must be equal to each other according to Rule 15. So if the size of this angle is beta, then the size of this angle must be also equal to beta because they are equal to each other according to Rule 15. So in total we found out that the big triangle AOD is similar to this small triangle POC according to angle similar to Rule. In both triangles we have angle theta, in both triangles we have angle alpha, and in both triangles we have angle beta. Therefore, triangle AOD is similar to this triangle POC according to angle similar to Rule. And for the fact that those two triangles are similar to each other, we can implement here Rule 22 that talks about two triangles that are similar to each other. So if it click on Rule 22 according to 22, the ratio of the areas of similar triangles is equal to the square of the ratio of their corresponding sides. So in the moment we have those two triangles. This is triangle ABC that is similar to this triangle DEF. And according to rule 22, the ratio between the areas of those two triangles, it is actually the area of this triangle ABC over the area of this triangle EDF. This is the ratio between the areas of those two triangles. That ratio is equal to the square of the ratio of their corresponding sides. Side AC is the corresponding side of side DE. So the ratio between the areas of those two corresponding sides is of course AC over DE squared. Likewise, side AB is the corresponding sides of side DF. And the ratio between the areas of those between those two corresponding sides is of course equal the square of the ratio of the areas of those two similar triangles of those two sides is equal to the AB over DF squared. Likewise, side CB is the corresponding side of side EF, and the ratio between the square of the ratio of those two corresponding sides is of course equal to CB over EF squared. So we can actually implement rule 22 in our drawing because of the fact that in our drawing we already found out that the big triangle AOD is similar to this small triangle POC. So we can implement here rule 22. According to rule 22, the ratio between the areas of those two triangles is actually the area of the big triangle AOD over the area of the small triangle COP. That ratio is equal to the square of the ratio of their corresponding sides. Here side AD is the corresponding side of side BC. So the square of the ratio of those two corresponding sides is of course AD over PC squared. AD over PC squared. So according to rule 22, the ratio between the areas of the two similar triangles is the area of triangle AOD over the area of triangle COP. And it is equal to the square of the ratio of their corresponding sides, that is actually AD over PC squared. This is the implementation of rule 22 in our drawing. The area of triangle AOD, the area of this triangle AOD is unknown, so we leave it as it is. Over the area of triangle COP. The area of this small triangle COP is 5, so we substitute the area of triangle COP by 5, and it is equal to AD is 2A, and PC is A. So AD over PC is 2A over A squared. We have to square it, so we have to square it here. We have A in the numerator and A in the denominator, so A will get cancelled, and therefore with 2 squared, that is 4. So in total, we found out that there are the big triangle AOD over 5 equals to 4. Here we multiply this equation by 5 and found out that the area of the big triangle AOD is equal to 5 times 4, that is 20 square roots. So the area of this big triangle AOD is equal to 20 square roots. Because of the fact that those two triangles are similar to each other, the following relationship exists between their sides. Side AD of this triangle ADO over side PC of this triangle POC is equal to side AO of this triangle AOD over side OC of this triangle COP. And again, side AD of the big triangle AOD over side PC of the small triangle COP is equal to side AO of the big triangle AOD over side OC of the small triangle COP. AD is 2A and PC is A. Again, AD is 2A and PC is A. So we have A in the numerator and A in the denominator, so A will get cancelled and we have to leave 2. And it is equal to AO over OC. We multiply this equation by OC and we found out that 2 times OC equals to AO. Here we define the length of line segment OC is B. We substitute OC by B in this equation and found out that actually the 2B equals to AO. So actually we found out that if the length of this side OC is B, then the length of this line segment AO is 2B. That is to say AO is twice as long as OC. In the next step I presented to you a new rule and I implemented the new rule in our drawing. The new rule is rule 23. Rule 23 is going in a triangle, so this is triangle ABC that could be any triangle. In this triangle ABC, if you draw line segment AP, it will divide the big triangle ABC into two small triangles. The first small triangle is triangle ABP and the second small triangle is triangle APC. Rule 23 talks about those two small triangles that were created by the line segment AP. According to Rule 23, the ratio between the areas of those two small triangles is actually the area of this triangle ABP over the area of this triangle APC. So that ratio is equal to the ratio between their corresponding sides. It's actually between their corresponding bases. The base of this triangle ABP is BP and the base of this triangle APC is PC. So it is BP over PC. Again, the ratio between the areas of those small triangles is equal to the ratio between their corresponding bases. It's actually BP over CP. Okay, so we can actually implement Rule 23 in our drawing. While put in our drawing, we have this is the right triangle ADC. In this right triangle ADC, we have line segment OD that divides the big right triangle ADC into two small triangles. The first small triangle is triangle ADO, and the second small triangle is triangle OGC. So all the requirements of Rule 23 are satisfied, and therefore we can implement here Rule 23. According to Rule 23, the ratio between the areas of those two small triangles is actually the area of triangle ADO over the area of triangle ODC. Again, the ratio between the areas of those two triangles is the area of triangle AOD over the area of triangle DOC. So that ratio is equal to the ratio between their corresponding bases. The base of triangle ADO is AO and the base of this triangle ODC is OC. So the ratio between their corresponding bases is of course AO over OC. AO over OC. So this equation is the implementation of Rule 23 in our drawing. Okay. So if we found out that according to Rule 23, the area of triangle AOD over the area of triangle DOC equals to AO over OC. We have already found out that the area of this big triangle AOD is 20. So substitute the area of triangle AOD by 20 over the area of this triangle DOC. The area of this triangle DOC is unknown, so we left it as it is. So it is 20 over the area of triangle DOC, and it is equals to AO over OC. AO is 2B and OC is B. So in total, AO over OC is 2B over B. We have B in the numerator and B in the denominator, so B is cancelled, and we left only with 2. So in total, we found out that 20 over the area of triangle DOC equals to 2. We multiply this equation by the area of triangle DOC and finally found out that 20 equals to 2 times the area of triangle DOC. Here we divided the equation by 2 and finally found out that the area of the small triangle DOC is equal to 20 over 2, that is 10. So the area of this small triangle DOC is equal to 10 square units. And it is very easy to say from the drawing that this triangle ABC can go into this right triangle ADC according to side rule. So all those two right triangles are similar, can go into each other. First of all, side AB equals to side DC because ABCD is a square. Likewise, side BC is equal to side AD for the same reason, and AC is the common side that belongs to both triangles. So in total, we have found out that all the sides of this triangle ABC are corresponding to all the sides are equal correspondingly to all the sides of this triangle ADC, and therefore those two rectangles can go into each other according to side rule. So again, if we found out that triangle ABC can go into triangle ADC according to side rule, and from the fact that those two triangles are similar to each other, we derive that they have also the same areas. That is to say, the area of triangle ABC is equal to the area of triangle ADC. But from the drawing it is very easy to see that the area of this triangle ADC in total equals to 20 plus 10, that is 30 square units. So you can write here that the area of triangle EDC equals to 30 square units, and from this equation, the area of triangle ABC equals to the area of triangle EDC equals to 30. We will derive that the area of triangle ABC is also equal to 30 square units. So, from one side, the area of this triangle ABC is equal to 30 square units, but from the other side, the area of this triangle ABC is equal to the area of the green shape plus 5, because the area of this triangle POC is 5. So we define the area of this green shape as x, that is to say the area of this green shape equals to x square units according to our definition, and therefore in total the area of this triangle ABC is equal to x plus 5 square units. So from the other side, the area of triangle ABC is equal to x plus 5 square units. And from this equation, x plus 5 equals to the area of triangle ABC equals to 30. We will derive that x plus 5 equals to 30. X plus 5 equals to 30. We subtracted 5 from this equation, and finally found out that x equals to 30 minus 5 is 25. X is the area of this green shape, so in total we have found out the area of this green shape, that is the area that we are looking for. This question is equal to 25 square units. Okay, thank you very much.